Welcome to The Explainer. So, have you ever looked up at a massive skyscraper, a sprawling concrete dam, or a gigantic bridge and wondered, how on earth is the ground actually holding all of that up? Well, today we're going to explore the hidden science of how the Earth supports our most massive structures without just completely collapsing under the pressure. Okay, here is a slightly terrifying but honestly amazing fact to kick things off. Every single heavy structure built on soil is destined to sink. Yep, it is an absolute inevitability. The real question isn't if it's going to sink, but how much. I mean, how do engineers know a building won't just keep sinking into the earth until it disappears? Well, somehow, before a single brick is even laid, they have to figure out exactly how much the ground is going to compress. Okay, let's dive into this. The geotechnical procedure used to compute these anticipated structural settlements is actually called settlement analysis. And this definition, it's going to be the anchor for our entire journey today. It is literally the mathematical and scientific process that stands between a perfectly stable, towering skyscraper and, well, a modern-day Leaning Tower of Pisa. To make sure we don't get lost in the weeds, here is our roadmap for today. 1. The goal of settlement analysis. 2. Gathering the subsurface data. 3. The 3 stages of settlement. 4. Flexible versus rigid foundations. 5. Variables that skew the math. And 6. The value of crude estimates. All right, sections 1 and 2, the goal and gathering the subsurface data. Let's look deep underground. You know, settlement analysis always operates on a very strict rule of 3. The whole procedure is meticulously divided into 3 parts. First, obtaining the soil profile. That's so we can understand the initial void ratio, specific gravity, and water content. Second, analyzing the transmission of stresses to the subsurface strata. Engineers use models like Boussinesq's theory for stress distribution for this, which, simply put, is essentially just a mathematical way to map how pressure spreads out through the dirt. And third, making the final settlement predictions, which is based on concepts from the theory of consolidation. So it always starts with gathering physical data, moves right into complex stress mathematics, and ends with calculating those final predictions. It is honestly awe-inspiring to think that this is how we view the Earth. This chart right here is exactly how engineers map the hidden unknowns beneath our feet. If you look at this typical soil profile, you can see these distinct layers, right? You've got medium sand at the top, a thick 25-meter layer of soft clay sitting in the middle, and fine sand down at the bottom. And notice how they meticulously track the different properties at different depths. For example, to compute the existing void ratio, they'll assume complete saturation below the water table. This data, which is extracted from undisturbed samples, is the raw fuel for absolutely all the math that follows. Moving on to section 3, the 3 stages of settlement. Here's what happens when we apply the foundation. Now that we actually have our data, this is where we shift our focus to what happens the exact moment a massive building is placed right on top of that specific soil profile we just mapped out. And look at this. We see another rule of 3 brilliantly illustrated in action here. The total settlement is made up of 3 distinct components. First up, there's the initial or elastic compression, which is sometimes called distortion settlement. This happens immediately upon the application of the foundation load. And what's wild about this is that in saturated soils, this immediate settlement happens purely as vertical soil compression, without any actual change in volume occurring first. Then, after that, comes consolidation or primary compression, which happens over time. And finally, you get secondary settlement. Now, what's really interesting about this slide is how real, hard math drives these estimates. We're looking at Skempton's 1951 influence factors. These are used to calculate the mean value of settlement for a rectangular foundation on a semi-elastic medium. Just look at how the influence factor changes based purely on the length-to-width ratio of the foundation. For a circle, it's 0.73. For a square, it's 0.82. And it just keeps going up as the shape stretches out. It really proves that there is precise geometry behind these calculations, keeping everything grounded without bogging us down in the really dense formulas. All right, section 4, flexible versus rigid foundations. Let's introduce a vital contrast in structural behavior. So, the math we just looked at doesn't just depend on the shape, it depends heavily on the structure's flexibility. This introduces a contrast in behavior that drastically changes how the math works and how pressure is distributed. Guide your eyes to the stark visual differences between these 2 curves. On the left side, we have a flexible building, like an earth embankment. Notice how the pressure it exerts downward is practically uniform. That's represented by those straight, equal arrows at the top. But look at the settlement pattern below it in the dashed lines. It causes this varying, bell-shaped settlement at the top of the buried compressible stratum. Now compare that to the rigid building on the right. It behaves completely differently. It forces a uniform, flat settlement curve below, but the actual contact pressure it exerts into the ground is highly varying. It gets incredibly intense right at the edges. Just to quickly summarize that fascinating paradox we just saw, a flexible foundation exerts practically uniform pressure but results in a varying bell-shaped settlement. Conversely, a rigid foundation forces a uniform, flat settlement but results in a highly varying contact pressure that is intense at the edges. It's crazy, right? Rigidity actually prevents uniform pressure. And understanding this contact pressure distribution is a massive headache and a major consideration for engineers because it entirely depends on the nature of the soil. Which brings us to Section 5, variables that skew the math. Because despite all that precise math, this is an imperfect science. Here is where the plot thickens a bit, because despite the precise tables and theoretical stress distributions we've covered so far, there are several real-world variables, curveballs really, that engineers have to account for. Things like construction loading periods, where engineers literally just have to use their judgment to decide what portion of a superimposed load will actually be sustained long enough to cause consolidation. Then there are deep foundations, where they might have to apply Fox's reduction factor, because standard theoretical calculations often overestimate settlement for deep digs. Oh, and don't forget lateral yielding, or horizontal drainage. Like as noted by Gould's 1946 investigations, horizontal drainage can make a clay layer settle way, way faster than standard one-dimensional math would ever predict. And that brings us to the giant elephant in the room. I have to use a slightly dramatic tone here because this is basically the great secret of geotechnical engineering. The mathematical theories of stress distribution used in all these analyses assume that the soil is perfectly elastic, perfectly homogeneous, and perfectly isotropic. But in reality, it practically never is. The very foundations of the stress transmission theories rely on conditions that simply do not exist in nature. Dirt is messy, it's layered, and it is entirely unpredictable. Finally, Section 6, the value of crude estimates. Let's resolve the tension between the complex math and the unpredictable dirt. So how do we resolve this immense tension between the highly complex math and the unpredictable, messy reality of the dirt beneath us? Well, I want to leave you with this incredibly humbling quote directly from our source material today. Settlement analyses usually give results which are at best crude estimates. However, even a crude estimate may be considered very much better than a pure guess or conjecture, which may be the only alternative. It's a profound realization, isn't it? The towering skyscrapers, the massive dams, the sprawling modern cities we live in, they all stand tall on this delicate balance of beautifully complex math and highly educated crude estimates. So the very next time you look up at a massive building and marvel at its height, I want you to look down at the ground and ask yourself, just how much is it sinking right now? Thank you for joining me on this explainer, and as always, keep learning.